Tonight we're going to explore something that sounds ridiculously simple, but hides one of the deepest questions in all of physics. Where does a photon get its color from? You've been told that light comes in colors: red light, blue light, green light. But here is the strange truth. Every single photon in the universe is the same kind of particle. There is no red particle and no blue particle. There is no pigment inside a photon. There is no tiny painted surface waiting to be seen. And yet, when a red photon and a violet photon arrive at your eye a millisecond apart, your brain registers two completely different colors. So what is actually different about them? What physical property does one photon carry that another does not? The answer touches everything from the inside of atoms to the machinery of your own eye, and it changes how you think about light. Before we go any further, if you find this kind of deep exploration fascinating, a quick like or subscribe really helps the channel grow. It's a small thing for you, but it makes a huge difference for me. Now, let's begin. Let's start with something that seems so obvious it barely deserves a question. Light has color. You see it every single day. The sky is blue, grass is green, a ripe strawberry is red. Sunsets paint the horizon in oranges and pinks and deep violets. You have lived your entire life surrounded by color, swimming in it, relying on it to navigate the world around you. Color is one of the most basic features of visual experience. It is so fundamental that most people never pause to wonder what it actually is. But tonight, we are going to pause. And when you look closely at what is actually happening when you see a color, when you strip away the familiarity and examine the physics underneath, you discover something deeply counterintuitive, something that challenges the way you have always thought about light. The light arriving at your eye is made of photons. Every beam of light, every glimmer of candlelight, every flash of lightning, every ray of sunshine breaking through a morning cloud is a stream of photons. And every single one of those photons is the same kind of particle. There is no red photon species and no blue photon species. There is no family of green photons that differs from the family of violet photons the way a cat differs from a dog. They are all photons. They are all excitations of the same electromagnetic field. They all travel at the same speed in a vacuum. They all have zero rest mass. They are all, at the most fundamental level, the same thing. Think about that for a moment. Every photon in the universe is the same type of particle. There is one photon type. One. Not dozens, not hundreds, not a different variety for each color of the rainbow. Just one. The photon that carries a radio broadcast across the Atlantic Ocean is the same kind of particle as the photon that lets you see the face of someone you love. The photon that warms your skin on a summer afternoon is the same kind of particle as the photon that a dentist uses to image your teeth. They are all photons. And yet one photon arrives at your eye and you see red. Another arrives and you see blue. A third arrives and your eye does not register it at all, because it falls outside the narrow band your biology can detect. So what is actually different about them? If they are all the same kind of particle, what physical property separates a photon that looks red from one that looks violet, from one that is completely invisible? The answer is not hidden in some exotic corner of physics. It is sitting right at the surface, but most people never slow down long enough to really think about what it means. The difference between a red photon and a blue photon is the same kind of difference as the one between a low note on a piano and a high note. It is frequency. That is the entire answer at the physical level. A photon's color, if you want to call it that, is its frequency. A photon that oscillates at a lower electromagnetic frequency carries less energy, and if it falls within the visible range, is perceived as red. A photon that oscillates at a higher frequency carries more energy, and if it falls within the visible range, is perceived as blue or violet. Every photon in the universe sits somewhere on a single continuous ladder of frequency, and the tiny sliver of that ladder your eyes happen to respond to is what you experience as the visible spectrum. That is what color is at the physical level, not a pigment, not a dye, not a substance painted onto the surface of a particle. It is a frequency of oscillation. This idea that color is a property of the light itself rather than something objects create has a history that stretches back centuries. In 1666, Isaac Newton performed one of the most famous experiments in the history of science. He darkened his room in Cambridge, cut a small hole in the window shutter to let in a thin beam of sunlight, and placed a glass prism in the path of that beam. The white sunlight entered the prism and emerged on the other side as a rainbow, a spectrum of colours spread across the wall. Red at one end, violet at the other, and every colour in between arranged in a smooth, continuous band. What Newton did next was the stroke of genius. He took a second prism and placed it in the path of one isolated colour from the first prism, say the green portion of the spectrum. When the green light passed through the second prism, it did not split into more colours. It stayed green. It bent, but it did not break down further. Green light was already a fundamental component. It could not be decomposed into anything simpler. Newton then took all the colours from the first prism and recombined them using a lens and a second prism. The result was white light again. White light, he concluded, is not a single thing. It is a mixture of all the spectral colours combined. The prism does not create colours. It separates colours that were already present in the white beam, hidden by their combination. This was a profound shift in understanding. Before Newton, most people assumed white light was pure and colours were modifications of it, that a prism somehow corrupted white light by adding colour. Newton showed the opposite. Colours are the fundamental components. White is the combination. The prism is just a tool that sorts them, bending each colour by a slightly different amount because each one travels at a slightly different speed through the glass. Newton did not know about photons or electromagnetic waves or frequencies. He could not have. Those concepts would not be developed for another 2 centuries. But he had discovered the essential truth that would later be understood in terms of frequency. What he called different colours were, in modern language, photons of different frequencies that had been travelling together in sunlight and were separated because they interacted differently with the glass. Let's unpack what frequency actually means for a photon, because this is where the picture becomes vivid and physical rather than abstract. A photon is not a tiny coloured ball flying through space like a microscopic paintball. It is a ripple in the electromagnetic field, a self-sustaining oscillation of electric and magnetic fields that propagates through space at the speed of light. As it travels, the electric field oscillates in one direction, while the magnetic field oscillates in a perpendicular direction. These oscillations are locked together, perfectly synchronized, each one generating the other as the disturbance moves forward. The number of times these fields complete a full cycle in 1 second is the frequency. That is what frequency means in this context. It is the rate of oscillation. How many times the electric and magnetic fields swing through a complete cycle every second. A red photon, the kind you might see from a laser pointer or the glowing element of an electric stove, oscillates its electric and magnetic fields roughly 430 trillion times every second. 430 trillion complete cycles in a single second. That is already an almost incomprehensibly large number. If you tried to count to 430 trillion at one number per second without sleeping or stopping, it would take you over 13 million years. And that is just the number of oscillations a red photon completes in 1 second. But a violet photon, at the opposite end of the visible spectrum, oscillates even faster, roughly 750 trillion times per second. The difference between red and violet, between the lowest and highest frequencies your eye can detect, is less than a factor of 2. The entire rainbow, every colour you have ever seen, Every sunset and flower and neon sign and firework fits inside a frequency range that does not even double from one end to the other. That is how narrow the visible window truly is. It is like having ears that can hear only a single octave on a piano and being deaf to everything else. Now, frequency and wavelength are two sides of the same coin, and understanding both is important for what comes later. When the frequency is lower, each cycle of oscillation takes longer to complete, and since the photon is moving at a constant speed, the distance between successive peaks of the wave is longer. That distance between peaks is the wavelength. Red light has a wavelength of roughly 700 nanometers. Violet light has a wavelength of roughly 400 nanometers. A nanometer is 1/1000th of a meter, extraordinarily small by everyday standards. You could line up roughly 100 red light wavelengths across the thickness of a single human hair. These wavelengths are real physical distances. If you could somehow freeze a red photon in place and measure the spacing between its electric field peaks, you would find about 700 nanometers. For a violet photon, about 400 nanometers. For a green photon sitting in the middle of the visible range, roughly 550 nanometers. The relationship between frequency, wavelength, and the speed of light is elegant and exact. The speed of light equals the frequency multiplied by the wavelength. Since the speed of light in a vacuum is a constant, roughly 300,000 kilometers per second, frequency and wavelength are locked in an inverse relationship. When one goes up, the other must come down. A photon cannot have both a high frequency and a long wavelength simultaneously. The two quantities are bound together by the speed of light, and that binding is absolute. But here is the crucial point that separates wavelength from frequency in importance. Wavelength can change. When a photon passes from a vacuum into glass or water or diamond, its speed decreases. Light moves slower in a medium than in empty space. This was confirmed experimentally long ago. Light travels roughly 1.5 times slower in glass than in vacuum, and about 1.3 times slower in water. And because the frequency stays the same while the speed drops, the wavelength must shrink to compensate. A photon of green light with a wavelength of 550 nanometers in air enters a glass lens, and its wavelength drops to roughly 367 nanometers inside the glass. But the frequency has not changed. The photon is still oscillating at the same rate. It is still the same photon carrying the same energy. When it exits the glass back into air, the wavelength stretches back to its original value. The photon emerges unchanged. The glass temporarily compressed the wavelength, but never altered the frequency or the energy. This is why frequency is the more fundamental identifier of what a photon actually is. Wavelength depends on the medium. Frequency does not. If you want to know the true identity of a photon, its essential physical character, do not ask about its wavelength, ask about its frequency. Two photons with the same frequency are physically identical in their energy content, even if one is currently traveling through a diamond and the other is crossing the empty space between galaxies. They carry the same energy. They will produce the same response in any detector sensitive to that frequency. The diamond has shortened the wavelength, but it has not touched the frequency or the energy. Frequency is the photon's fingerprint. It is the one property that never changes as the photon passes through different materials and different environments. And this brings us to energy, which is the deepest layer of the answer. A photon's frequency is not just some abstract oscillation rate, a number you write down and move on from. It is directly and exactly proportional to the photon's energy. This proportionality was one of the most revolutionary discoveries in the history of physics, and it was the spark that ignited quantum mechanics itself. In the year 1900, the German physicist Max Planck was wrestling with a problem that had defeated some of the best minds in physics for decades. The problem was deceptively simple in its setup. When you heat an object, it glows. A piece of iron in a blacksmith's forge starts dark, then glows a dull red, then a brighter orange, then yellow, then white as the temperature rises. This progression is not random. Hotter objects glow at higher frequencies. Physicists wanted to calculate exactly how much light a hot object emits at each frequency. They had equations from classical physics, but those equations gave absurd results. They predicted that a hot object should emit infinite energy at high frequencies. The math said that every warm object in the universe, every cup of coffee, every human body, should be blasting out lethal amounts of ultraviolet and gamma radiation at all times. This was so clearly wrong that physicists gave it a name: the ultraviolet catastrophe. The theory predicted a catastrophe that obviously was not happening. Something was fundamentally broken in the classical picture of light. Planck found the fix, and in doing so, he changed the course of physics forever. He proposed that the energy of electromagnetic radiation is not continuous. It does not come in any arbitrary amount you please. Instead, energy comes in discrete packets, tiny indivisible units, and the energy of each packet is proportional to the frequency. Higher frequency means more energy per packet. Lower frequency means less. The proportionality constant linking energy to frequency is now called Planck's constant, and it is one of the most fundamental numbers in all of nature. Its value is extraordinarily small, roughly 6.63 times 10 to the negative 34 joule seconds. That tiny number is the reason quantum effects are invisible in everyday life. The packets of energy are so small at everyday frequencies that they blend together into what appears to be a smooth, continuous flow. But for individual photons, Planck's constant is everything. It determines how much energy each one carries. The equation is direct and profound. Energy equals Planck's constant times frequency. A photon with twice the frequency carries exactly twice the energy. A photon with 10 times the frequency carries exactly 10 times the energy. There is no ambiguity, no wiggle room, no exceptions. Frequency and energy are locked together in perfect proportionality, and Planck's constant is the unchanging bridge between them. This single equation connects the physical oscillation rate of a photon's electromagnetic fields to the amount of energy it delivers when it is absorbed. It is one of the most important equations in all of physics. This means that when we say a photon is red, we are really saying three things simultaneously. We are saying it has a relatively low frequency within the visible range. We are saying it has a relatively long wavelength. And we are saying it carries a relatively small amount of energy compared to photons at the blue and violet end of the spectrum. A single violet photon carries roughly 1.7 times the energy of a single red photon. That might not sound like much, but the consequences are enormous. It is the reason ultraviolet photons can damage your DNA, while red photons cannot. It is the reason X-ray photons can penetrate your body and image your bones, while visible light cannot. The energy difference between frequencies is not just an abstraction written in a textbook. It determines what a photon can physically do when it interacts with matter. 5 years after Planck's breakthrough, Albert Einstein took the idea further in a direction that stunned the physics community. In 1905, Einstein proposed that light itself is quantized. Not just the emission and absorption of light, as Planck had carefully limited himself to suggesting, but the light itself travelling through space. Each photon is a single indivisible quantum of electromagnetic energy. You cannot have half a photon. You cannot split a photon into two smaller pieces with lesser energies while keeping the same frequency. A photon is the minimum possible unit of light at a given frequency. It is all or nothing. Einstein used this idea to explain the photoelectric effect, an experiment that had been baffling physicists for years. When you shine light on certain metal surfaces, electrons can be knocked free. This was known. But the strange thing was that the energy of the ejected electrons did not depend on how bright the light was. It depended on the frequency. Dim violet light could eject electrons with high energy. Bright red light could not eject electrons at all, no matter how intense the beam. You could shine the brightest red spotlight imaginable on the metal surface and wait as long as you wanted, and not a single electron would be freed. But a faint violet glow would knock electrons loose immediately. Classical physics could not explain this. If light were a continuous wave, then brighter light should deliver more energy to each electron, and eventually, any color of sufficiently bright light should be able to free them. Einstein's explanation was simple and devastating to the classical picture. Each photon arrives as a single discrete packet of energy. The energy of that packet is determined by the frequency and nothing else. If the frequency is too low, if the individual photon does not carry enough energy to overcome the forces binding the electron to the metal, then nothing happens. No electron is ejected. It does not matter how many low-energy photons you send. Each one interacts individually with the material, and each one individually fails to deliver enough energy to free an electron. It is like trying to break down a heavy door by throwing cotton balls at it. You can throw 1,000,000 cotton balls, and the door will not budge, because each individual impact carries too little energy. But a single bullet, a single concentrated impact with enough energy, goes right through. A single high-frequency photon carries enough energy to knock an electron free. Brightness determines how many photons arrive per second. Frequency determines how much energy each individual one carries. These are completely independent properties of a beam of light. This was the moment physics truly began to understand what a photon's color really is at the deepest level. Color is not a substance painted onto the photon. It is not a material wrapped around it like pigment on a wall or dye in fabric. It is the energy the photon carries, expressed as an electromagnetic frequency. A red photon and a violet photon are the same kind of entity, the same type of excitation in the same electromagnetic field, but one vibrates slower and carries less energy, while the other vibrates faster and carries more. That is the only physical difference between them. Now let's zoom out and look at the full electromagnetic spectrum, because the visible colors are only a tiny fragment of a much larger reality. The electromagnetic spectrum stretches from the lowest imaginable frequencies to the highest, spanning more than 20 orders of magnitude. At the very bottom are radio waves. These are photons with frequencies as low as a few thousand hertz and wavelengths that can stretch for kilometers or even longer. Your car radio antenna detects these photons. They carry incredibly tiny amounts of energy per individual photon. A single radio wave photon has so little energy that detecting it individually is extraordinarily difficult. Radio telescopes and radio receivers work by collecting enormous numbers of them simultaneously, pooling the energy from billions upon billions of photons to create a detectable signal. Moving up in frequency, you reach microwaves. These are the photons your microwave oven uses, with frequencies in the billions of hertz and wavelengths measured in centimeters. They carry more energy per photon than radio waves, but still far less than visible light. The cosmic microwave background radiation, the faint afterglow of the Big Bang that fills every corner of the observable universe, consists of microwave photons that have been traveling through space for roughly 13.8 billion years. Those ancient photons began as high-energy radiation in the hot, early universe and have been stretched by the expansion of space over billions of years until they now sit in the microwave range. Then comes infrared. Infrared photons have frequencies just below the visible range. You cannot see them, but you can feel them as heat. When you hold your hand near a campfire and feel warmth radiating onto your skin, even though you are not touching the flames, that warmth is infrared photons striking your skin and transferring their energy to it. Every warm object emits infrared photons. Your own body is constantly radiating infrared light, glowing in a frequency range your eyes are blind to. Night vision devices work by detecting this invisible infrared glow, turning it into a visible image. Then comes the visible spectrum, a razor-thin band of frequencies where the electromagnetic field happens to interact with the photoreceptor molecules in the human retina. Red, orange, yellow, green, blue, violet. The entire rainbow of colors you have ever perceived in your life occupies roughly 1 octave of frequency, from about 430 trillion Hz to about 750 trillion Hz. In the vast continuum of electromagnetic frequencies, spanning more than 20 orders of magnitude, this visible window is absurdly narrow. It is a sliver so thin that it barely registers on a full diagram of the spectrum. Above visible light comes ultraviolet. These photons have higher frequencies and more energy per photon than violet light. They carry enough energy to break chemical bonds in biological molecules, which is why prolonged ultraviolet exposure causes sunburn, premature skin aging, and can damage the DNA inside your cells. The sun emits a substantial amount of ultraviolet radiation, but Earth's ozone layer absorbs most of the highest energy ultraviolet photons before they reach the surface. Without that ozone shield, life on land as we know it would face constant radiation damage. Above ultraviolet come X-rays, with frequencies in the quintillions of hertz and wavelengths smaller than the diameter of an atom. They carry enough energy to penetrate soft tissue, which is why they are used in medical imaging. Your bones absorb X-rays more readily than your muscles and organs, creating contrast on an image. And at the very top of the spectrum are gamma rays, the highest frequency, highest energy photons in the universe. They are produced in nuclear reactions, in the annihilation of matter and antimatter, and in the most violent astrophysical events in the cosmos. A single gamma ray photon can carry millions of times more energy than a single photon of visible light. And here is what ties all of this together into one profound realization. Every single one of these, from the lowest frequency radio wave to the highest energy gamma ray, is a photon. They are all the same fundamental particle. They are all excitations of the same electromagnetic field. They all travel at the same speed in a vacuum. They all have zero rest mass. They all obey the same laws of physics. The only thing that differs is the frequency, and therefore the energy, and therefore the wavelength. That is it. There is no structural difference between a radio wave photon and a gamma ray photon. One simply oscillates incomparably faster than the other, and carries incomparably more energy. The same entity that gently carries a voice across a radio broadcast is, at a different frequency, the same entity that can shatter molecular bonds inside a living cell. The electromagnetic spectrum is not a collection of different things. It is one thing, the photon, playing an almost infinite range of notes. The boundaries between radio and microwave, between infrared and visible, between ultraviolet and X-ray, are not physical walls separating different species of particle. They are labels humans invented for convenience. Nature draws no line between red and infrared. There is no barrier a photon crosses when it shifts from being visible to being invisible. The spectrum is continuous and seamless. Every frequency is occupied. Every energy is possible. The boundaries are ours, not nature's. And this raises the question that will carry us forward. If a photon's color is really just its frequency and its energy, then where does that particular frequency come from? Something must set it. When a photon is born, when it springs into existence from an atom or a star or a glowing filament, something determines whether it will oscillate at the frequency of red light, or blue light, or invisible infrared. Something in the source chooses the note. The photon does not choose its own frequency, any more than a musical note chooses its own pitch. The physics of whatever created the photon does the choosing. and the mechanisms that set that frequency, the quantum transitions inside atoms, the thermal agitation of hot matter, the acceleration of charged particles, are some of the most elegant processes in all of nature. The question at the heart of everything we are about to explore is deceptively simple. When a photon is created, what decides its frequency? We established that frequency is the photon's fundamental identity, the physical property that determines its energy, and, for visible light, the color we perceive. But frequency does not appear from nowhere. Something in the physical world has to produce a photon at one specific frequency rather than another. Something has to set the note. And the most precise, most elegant mechanism for setting that note happens inside individual atoms. To understand how atoms produce photons with specific frequencies, you first need to understand something about atoms that was not obvious to anyone before the 20th century. The electrons inside an atom cannot have just any energy they please. They are restricted to specific energy levels, like steps on a staircase. An electron can stand on the first step, or the second step, or the fifth step, but it cannot stand between steps. There is no halfway point. The electron is either on one level or another. It cannot exist in the space between them. This is one of the central discoveries of quantum mechanics, and it was shocking when it was first proposed, because nothing in everyday experience works this way. When you climb a ramp, you can stop at any height you choose. But an electron inside an atom is not on a ramp. It is on a staircase with fixed steps, and those steps are determined by the laws of quantum mechanics and the specific structure of the atom. In 1913, the Danish physicist Niels Bohr proposed this model to explain a puzzle that had been nagging physicists for decades. When you heat a gas of pure hydrogen and look at the light it emits through a prism, you do not see a smooth, continuous rainbow. You see individual lines, specific narrow bands of colour separated by darkness. Hydrogen emits a red line, a blue-green line, a blue-violet line, and several more in the ultraviolet that the eye cannot see. These lines are sharp and precise. The red line is always at exactly the same wavelength, roughly 656 nanometers. The blue-green line is always at roughly 486 nanometers. They never shift, they never blur, they are as precise as a fingerprint. Before Bohr, no one could explain why hydrogen emits these particular wavelengths and no others. Classical physics predicted that an electron orbiting a nucleus should be able to have any energy and should therefore emit light at any frequency, producing a smooth, continuous spectrum. Worse, classical physics predicted that the electron should continuously radiate energy as it orbits, spiraling inward and crashing into the nucleus in a tiny fraction of a second. Atoms should not be stable at all, according to classical physics. And yet atoms clearly are stable. They persist for billions of years. Something was deeply wrong with the classical picture. Bohr's insight was that the electron in a hydrogen atom can only occupy certain discrete energy levels. It cannot spiral smoothly inward because there is a lowest level, a ground state, below which the electron cannot go. The electron is trapped on the staircase. It can move between steps, but it cannot slide between them, and it cannot fall off the bottom. When the electron drops from a higher level to a lower level, it must release exactly the amount of energy equal to the difference between those two levels. That energy is carried away by a single photon, and because the energy gap between the levels is fixed, the photon's energy is fixed. And because a photon's energy equals Planck's constant times its frequency, the frequency is fixed. The atom does not have a choice. The energy gap dictates the frequency, period. Think of it like a ball on a staircase. If a ball rolls from the fifth step down to the third step, it loses a specific amount of height, and that height determines how much energy the ball gains as it falls. The ball cannot lose a random amount of height. It can only lose the exact difference between step 5 and step 3. An electron inside an atom works the same way. When it drops from one energy level to another, the photon it emits carries exactly the energy of that gap. No more, no less. The photon's frequency is stamped by the size of the quantum jump. This is why hydrogen always emits that specific red line at 656 nanometers. That line corresponds to an electron falling from the third energy level to the second energy level. The energy difference between those two levels in hydrogen is always the same. So the photon produced always has the same frequency, and therefore the same wavelength and the same color. It is called the hydrogen alpha line, and it is one of the most important spectral lines in all of astronomy. When you see photographs of glowing nebulae in space, those vast clouds of gas glowing red and pink, that red light is almost entirely hydrogen alpha. It is the same transition happening in trillions upon trillions of hydrogen atoms simultaneously, each one independently dropping an electron from level 3 to level 2 and emitting a photon at exactly the same frequency. The hydrogen atom produces other lines as well. An electron falling from the fourth level to the second produces a blue-green photon at roughly 486 nanometers. From the fifth level to the second, a blue-violet photon at roughly 434 nanometers. From the sixth level to the second, a violet photon at roughly 410 nanometers. Each transition produces a photon at its own specific frequency. Together, these lines form what physicists call the Balmer series, the set of hydrogen emission lines that fall in the visible range. There are also hydrogen lines in the ultraviolet, produced by electrons falling down to the first level, and lines in the infrared, produced by electrons falling to the third level or lower. The entire pattern of hydrogen emission lines was one of the great triumphs of early quantum mechanics, because Bohr's model predicted every single one of them with extraordinary accuracy. Now, different elements have different atomic structures. They have different numbers of protons in their nuclei, different numbers of electrons, and therefore different energy level structures. The spacing between energy levels in hydrogen is different from the spacing in helium, which is different from sodium, which is different from iron, which is different from every other element. This means every element emits its own unique set of spectral lines, its own fingerprint of frequencies. Sodium, for example, has a pair of closely spaced energy transitions that produce photons in the yellow part of the spectrum at wavelengths of roughly 589 nanometers. If you have ever seen the orange-yellow glow of old-fashioned streetlights, you have seen sodium emission lines. Those lamps contain sodium vapor, and when electricity excites the sodium atoms, their electrons jump to higher energy levels and then fall back down, emitting photons at sodium's characteristic yellow frequencies. The color is not a design choice, it is physics. Sodium atoms can only emit at frequencies determined by their energy level structure, and the strongest visible transitions happen to fall in the yellow. Neon works the same way. Neon signs glow their distinctive red-orange because neon atoms have energy level transitions that produce photons concentrated in the red and orange part of the visible spectrum. When electricity passes through a tube filled with neon gas, the neon atoms are excited, and when their electrons drop back to lower energy levels, they emit photons at neon's characteristic frequencies. Different gases produce different colors because they have different energy level structures. Argon produces a pale lavender. Krypton produces a whitish green. Mercury vapor produces a strong blue-violet. Helium produces a pale peach. Each element announces its identity through the specific frequencies of light it emits, and those frequencies are set entirely by the quantum mechanical structure of the atom. This principle extends far beyond glowing gas tubes. It is one of the most powerful tools in all of science. In the 1860s, Gustav Kirchhoff and Robert Bunsen demonstrated that you could identify elements by the light they emit when heated. Put an unknown substance in a flame, spread the light through a prism, and examine the spectral lines. If you see sodium's characteristic yellow doublet, sodium is present. If you see hydrogen's red, blue-green, and violet lines, hydrogen is present. Each element leaves its unmistakable signature in light. This technique, called spectroscopy, transformed chemistry and astronomy alike. On Earth, it lets chemists identify the composition of materials without touching them. In astronomy, it lets scientists determine what distant stars, nebulae, and galaxies are made of by analyzing the light they emit. But the story of spectroscopy actually began even earlier, with the discovery that seemed like a flaw in sunlight. In 1814, the German optician Joseph von Fraunhofer built the finest prisms and diffraction gratings of his era and turned them on the sun. When he spread sunlight into its spectrum with extraordinary precision, he found something no one had noticed before. The smooth rainbow of solar colors was interrupted by hundreds of dark lines, narrow gaps where specific frequencies were missing from the sunlight. These dark lines appeared at exactly the same positions every time he looked. They were not smudges or imperfections, they were real absences, specific frequencies that were present in the deeper layers of the sun but had been removed before the light reached Earth. Fraunhofer catalogued hundreds of them. He did not know what caused them, but he mapped them with meticulous care. Decades later, Kirchhoff and Bunsen provided the explanation. The dark lines in the solar spectrum matched the bright emission lines of known elements. The dark line at the exact position of sodium's yellow emission corresponded to sodium absorbing those frequencies in the sun's outer atmosphere. Light from the sun's hot interior contains all frequencies, but as that light passes through the cooler gas in the sun's outer layers, atoms in that gas absorb photons at their characteristic frequencies, the same frequencies they would emit if excited. The absorbed frequencies are removed from the beam, leaving dark gaps in the spectrum. So the same quantum energy levels that cause an atom to emit light at specific frequencies also cause it to absorb light at those same frequencies. Emission and absorption are two sides of the same coin, both governed by the same set of energy levels. This means every element in the periodic table has been catalogued with its unique set of spectral lines. When astronomers point a telescope at a distant star and spread its light into a spectrum, they can read the chemical composition of that star's atmosphere from the pattern of emission and absorption lines. They can detect hydrogen, helium, carbon, oxygen, iron, and dozens of other elements across distances of thousands of light years. The frequency of each spectral line tells them which element produced it. The brightness of each line tells them how much of that element is present. All of this information is encoded in the frequencies of the photons that arrive at the telescope, frequencies that were set by quantum transitions inside atoms on the surface of a star that may be inconceivably far away. But atoms are not the only things that emit photons. Molecules do too, and they add another layer of complexity. A molecule is a collection of atoms bonded together, and molecules have their own internal energy states beyond just the electronic levels of individual atoms. Molecules can vibrate. The bonds connecting the atoms act like tiny springs, and the atoms can oscillate back and forth. These vibrational states are also quantized, meaning the molecule can only vibrate at certain specific energies. When a molecule drops from a higher vibrational state to a lower one, it emits a photon whose frequency corresponds to the energy gap between those vibrational levels. The energy gaps for molecular vibrations are smaller than those for electronic transitions in atoms, so the photons produced tend to have lower frequencies. Most molecular vibrational transitions produce photons in the infrared part of the spectrum, below the range of human vision. Molecules can also rotate. A diatomic molecule like carbon monoxide can spin end over end, and the rotational energy is quantized as well. Rotational transitions produce photons with even lower energies and lower frequencies than vibrational transitions, typically in the microwave or far infrared range. The specific frequencies of these rotational and vibrational transitions depend on the masses of the atoms in the molecule, the strength of the bonds, and the geometry of the molecule. Each molecule has its own set of vibrational and rotational spectral lines, just as each atom has its own electronic spectral lines. Carbon dioxide absorbs and emits infrared photons at specific frequencies, determined by its molecular vibrations. This is directly relevant to life on Earth, because the absorption of infrared photons by carbon dioxide in the atmosphere is the physical mechanism behind the greenhouse effect. Infrared photons emitted by Earth's surface are absorbed by carbon dioxide molecules, which then re-emit them in random directions, some back toward the surface. The specific infrared frequencies at which carbon dioxide absorbs are set by the quantum mechanics of its molecular vibrations. The greenhouse effect is, at its root, a consequence of the discrete energy levels inside a molecule. There is another molecular process that deserves attention because it demonstrates something important about how the emitting system controls the frequency of the photon that comes out. It is called fluorescence. A molecule absorbs a photon at one frequency, usually ultraviolet, and then re-emits a photon at a lower frequency, often in the visible range. The frequency of the emitted photon is not the same as the frequency that went in. The molecule absorbs the incoming photon, and the energy kicks an electron to a high excited state. But instead of dropping straight back down, the electron first loses some energy through internal vibrations, non-radiative steps that dissipate a portion of the absorbed energy as heat. Then the electron drops the remaining distance and emits a photon whose energy matches only that smaller gap. A smaller energy gap means a lower frequency. The output frequency is determined entirely by the molecular energy level structure, not by whatever frequency went in. This is why a blacklight poster glows vivid colors under an ultraviolet lamp. The ultraviolet photons are invisible to your eye, but the fluorescent dyes in the poster absorb them and re-emit visible photons at frequencies set by the dye molecules. Certain minerals in museum displays do the same thing, absorbing ultraviolet and glowing green or orange or blue. Laundry detergents contain optical brighteners that absorb ultraviolet from sunlight and re-emit blue-violet visible photons, which is why freshly washed white clothes can appear almost unnaturally bright. In each case, the emitted photon's frequency is not a copy of what was absorbed. It is a new frequency, written by the energy level structure of the molecule that did the absorbing. The source still writes the note. It simply writes a different note than the one it received. Now let us move from individual atoms and molecules to something broader. Not every source of light produces neat spectral lines. When you look at the glowing filament of an incandescent light bulb, or the surface of a star, or the embers of a campfire, you see light spread across a wide, continuous range of frequencies, rather than concentrated at specific lines. This is thermal radiation, and it arises from a different mechanism than the discrete quantum jumps we have been discussing. Physicists use the term black-body radiation to describe the idealized version of this phenomenon. A perfect blackbody is an object that absorbs all electromagnetic radiation that falls on it and re-emits that energy as thermal radiation, whose spectrum depends only on the object's temperature. No real object is a perfect blackbody, but many come close. Stars are excellent approximations. The filament of an incandescent bulb is a reasonable one. A kiln with a small opening, where light enters and bounces around inside until it is completely absorbed and re-emitted thermally, is nearly perfect. The spectrum that emerges from such a source has a very specific shape, a smooth curve that rises from zero at low frequencies, peaks at a frequency determined by the temperature, and then falls off again at higher frequencies. This curve was the very thing Planck was trying to calculate in 1900 when he introduced the idea of energy quanta. In any object with a temperature above absolute zero, the atoms and molecules are in constant thermal motion. They vibrate, they jostle, they collide with each other. In a solid or a dense gas, these collisions are happening constantly, billions of times per second for each particle. Every collision can change the energy state of the particles involved. Electrons get bumped to higher levels, then fall back down. Molecules are excited into higher vibrational states, then drop back. Charged particles accelerate and decelerate as they bounce off each other. All of these processes produce photons, and because the collisions happen at a vast range of energies, the photons produced span a broad, continuous range of frequencies rather than appearing at specific lines. The result is a characteristic spectrum that depends primarily on one thing: the temperature of the object. A cooler object emits mostly at lower frequencies. A hotter object emits at higher frequencies. This is not an approximation or a rough trend. It is a precise mathematical law. The German physicist Wilhelm Wien worked out a key piece of this in 1893 with what is now called Wien's displacement law. It states that the peak frequency of thermal radiation, the frequency at which the object emits the most energy, is directly proportional to the temperature. Double the temperature and the peak frequency doubles. Triple the temperature and the peak frequency triples. The relationship is clean and exact. This is why hot objects change color in a predictable sequence as they heat up. A piece of iron at room temperature emits thermal radiation, but the peak frequency is far in the infrared, invisible to your eyes. The iron looks dark. Heat it to roughly 500 degrees Celsius, and the peak frequency shifts upward. The iron begins to emit a small amount of visible light at the red end of the spectrum. It glows a dull red, just barely visible. Heat it further to roughly 1000 degrees Celsius, and the peak shifts higher. More visible light is emitted, and the glow brightens to a cherry red, then an orange red. At roughly 1200 degrees Celsius, it glows bright orange. At roughly 1500 degrees, a yellowish white. If you could heat it even further without it melting or vaporizing, it would glow white, then blue-white, emitting strongly across the entire visible range and peaking in the blue. This progression from invisible infrared to dull red to orange to yellow to white to blue-white is universal. It applies to any dense hot object. A candle flame glows orange and yellow because the tiny soot particles in the flame are heated to roughly 1000 to 1500 degrees Celsius. A tungsten light bulb filament operates at roughly 2500 degrees Celsius, giving it a warm, yellowish-white glow. The surface of our Sun has a temperature of roughly 5500 degrees Celsius, and its thermal radiation peaks right in the middle of the visible spectrum, in the green-yellow range. This is not a coincidence. Human eyes evolved under sunlight, so it makes sense that our vision is most sensitive to the frequencies the Sun emits most strongly. But here is where it connects back to everything we have discussed. The Sun does not emit light at a single frequency. Its thermal spectrum is a broad, smooth curve, spanning infrared through visible through ultraviolet. The peak is in the visible range, but there is substantial emission on both sides of the peak. This is why sunlight appears white to our eyes. It is not because there is a special white frequency. There is no white photon. White is what you perceive when many frequencies across the visible spectrum arrive at your eye simultaneously in a roughly balanced mixture. The Sun emits red photons and orange photons and yellow photons and green photons and blue photons and violet photons all at once in enormous numbers, and your eye receives them all together, and your brain combines them into the sensation of white light. That white light is a composite, not a single frequency. When Newton passed it through a prism, he separated those component frequencies and revealed the rainbow that was always there, hidden by the combination. Stars hotter than our Sun have higher surface temperatures, which means their thermal radiation peaks at higher frequencies. A star with a surface temperature of 10,000 degrees Celsius peaks in the blue part of the spectrum and appears blue-white. A star at 20,000 degrees peaks in the ultraviolet, but because it still emits plenty of blue visible light, it appears deep blue to the human eye. Stars cooler than our Sun peak at lower frequencies. A red dwarf star with a surface temperature of roughly 3,000 degrees Celsius peaks in the infrared, and most of its visible emission is concentrated at the red end of the spectrum, giving it a distinctly reddish color. A red giant star, like the famous Betelgeuse in the constellation Orion, has a surface temperature of roughly 3,400 degrees Celsius, and it glows a deep red-orange for exactly this reason. Its thermal radiation peaks in the infrared, and the visible light it does emit is dominated by red frequencies. The color of a star is a direct thermometer. Astronomers can estimate a star's surface temperature just by looking at its color. Blue stars are hot. White stars are moderately hot. Yellow stars like our Sun are medium. Orange stars are cooler. Red stars are the coolest visible stars. This color-temperature relationship is not a rough guide. It is a precise physical law rooted in the quantum mechanics of thermal radiation, the same physics Planck wrestled with in 1900. There is a beautiful unity here. Whether you are looking at a neon sign, a sodium street lamp, a candle flame, or a distant star, the same principle is at work. The frequency of the photon is determined by the physics of the emitting system. For an isolated atom in a gas, the frequency is set by the energy gap between two quantum levels. The atom can only emit photons whose energies match the spacing of its staircase. For a hot, dense object like a star or a glowing filament, the frequency distribution is set by the temperature, which determines the statistical spread of energies among the trillions of colliding particles inside the material. In both cases, the photon's frequency is not a random accident. It is a consequence of the physical conditions at the source. The atom's structure dictates the line, the temperature dictates the curve, and in both cases, Planck's constant ties the frequency to the energy. There is one more mechanism worth understanding because it plays a role in many natural and artificial sources of light. When a charged particle is accelerated, it emits electromagnetic radiation. This is a fundamental result from classical electrodynamics, confirmed experimentally countless times. If you shake an electron back and forth, it produces a photon. The frequency of the photon depends on how rapidly the electron is accelerated. Fast, violent accelerations produce high-frequency photons. Slow, gentle oscillations produce low-frequency photons. This is how a radio antenna works. Electrons are driven back and forth along the antenna by an alternating current. As they accelerate and decelerate, they emit electromagnetic radiation at the frequency of the current driving them. A radio station broadcasting at 100 MHz drives electrons in its antenna at 100 million cycles per second, and the photons produced oscillate at exactly that frequency. The antenna is choosing the photon's frequency by choosing how fast to shake the electrons. Change the station and you change the oscillation rate, which changes the frequency of the photons produced. The photon has no say in the matter. It simply takes whatever frequency the source dictates. In nature, this mechanism produces a wide variety of photon frequencies. In the sun's corona, electrons spiraling along magnetic field lines emit X-ray and ultraviolet photons. In the hot gas surrounding a black hole, charged particles accelerated to enormous speeds produce gamma rays. In a lightning bolt, the rapid acceleration of electrons through air produces a brief flash that spans a wide range of frequencies from radio waves to visible light. In every case, the frequency of the emitted photon is determined by how violently and how rapidly the charged particle was accelerated. So now we can answer the question we started with in full. Where does a photon get its frequency? From the physics of whatever created it. If an electron drops between energy levels in an atom, the photon's frequency equals the energy gap divided by Planck's constant. If the photon comes from a hot object radiating thermally, the distribution of frequencies is set by the temperature, with the peak frequency proportional to the temperature. If the photon comes from an accelerating charged particle, the frequency depends on the rate and nature of the acceleration. In every case, the photon's frequency is not a random selection from an infinite menu. It is determined, precisely and inevitably, by the physical process that created it. The source writes the note, the photon simply carries it. And here is what we should take away before we move on. A photon does not choose to be red. It does not decide to be blue. It does not contain a hidden mechanism that selects its frequency after it is born. The frequency is fixed at the moment of creation, and it never changes during the photon's journey through empty space. A red photon emitted by a hydrogen cloud 10,000 light-years away arrives at Earth still red, still oscillating at the same frequency it had when it was born, still carrying the same energy it was given in that original quantum jump. The frequency is the photon's birth certificate, written by the atom or molecule or hot surface or accelerating charge that created it, and it remains unchanged unless something along the journey acts upon it. Whether anything can change that frequency, and what it means when it does change, is the next piece of the story. So far, we have been talking about emission, about atoms and hot surfaces and accelerating charges, creating photons and stamping each one with a specific frequency. But most of the colors you see in daily life do not come from emission at all. The red of a fire truck, the green of a leaf, the blue of your favorite shirt, the brown of a wooden table. None of these objects are emitting visible light. They are not glowing. They are not hot enough to produce visible thermal radiation. The fire truck is not a tiny star. The leaf is not a neon tube. So where does their color come from? The answer is reflection and absorption, and understanding it requires a shift in thinking, because the mechanism that gives a leaf its green color is fundamentally different from the mechanism that gives a sodium lamp its yellow glow, or a hot star its blue-white brilliance. Emission color comes from the source. It is the photon being born at a specific frequency. Reflected color comes from a filter. It is the source producing a broad mixture of frequencies, and the object selectively removing some of those frequencies and bouncing the rest toward your eye. The photons you see from a red apple were not created by the apple. They were created by the sun, or by whatever lamp is illuminating the room. The apple merely decided which of those photons to keep and which to send back. Start with sunlight. As we discussed, the sun emits a broad thermal spectrum that spans the entire visible range and beyond. Sunlight is not yellow, despite the way children draw it in crayon. Sunlight is white, a roughly balanced mixture of red, orange, yellow, green, blue, and violet photons arriving simultaneously in enormous numbers. When that white sunlight strikes an object, some frequencies are absorbed by the material and some are reflected. The specific mix of frequencies that bounces back toward your eye depends on the chemical and physical structure of the object's surface. That reflected mix of frequencies is what you perceive as the object's color. Consider a ripe tomato. When white sunlight hits the tomato's skin, the chemical compounds in the skin, primarily a pigment called lycopene, absorb photons across most of the visible spectrum. Blue photons are absorbed. Green photons are absorbed. Yellow photons are mostly absorbed, but red photons are not absorbed efficiently. They bounce off the surface and travel to your eye. Your eye receives mostly red frequency photons from the tomato, and your brain registers the sensation of red. The tomato is not emitting red light. It is subtracting everything except red from the white light that illuminated it. The color you see is what is left over after absorption has done its work. A leaf works the same way, but with a different pigment. Chlorophyll, the molecule responsible for photosynthesis, absorbs red and blue light efficiently because those frequencies carry the right amount of energy to drive the chemical reactions of photosynthesis. Green light is not absorbed as strongly. It reflects off the leaf and reaches your eye, so the leaf appears green. This is not because the leaf generates green photons. It is because the leaf removes red and blue photons from the sunlight and returns the green ones. The color of the leaf is determined by the molecular structure of chlorophyll, which determines which frequencies are absorbed and which are not. A white object reflects nearly all visible frequencies without strong selectivity. When white sunlight hits a white cotton shirt, the fibers scatter and reflect photons across the full visible range roughly equally. Your eye receives a balanced mix of all visible frequencies, and your brain interprets that balanced mix as white. A black object does the opposite. It absorbs nearly all visible frequencies and reflects almost nothing. Very few photons reach your eye, and you perceive the absence of reflected light as black. Black is not a frequency. It is the near total absence of reflected visible photons. What happens to the photons that are absorbed? They do not vanish. Energy is conserved. When a pigment molecule absorbs a photon, the photon's energy is converted into other forms, usually vibrational energy in the molecule, which ultimately becomes heat. A black car parked in direct sunlight gets hot precisely because it is absorbing photons across the visible spectrum and converting their energy into thermal motion. A white car stays cooler because it reflects most of those photons instead of absorbing them. The energy bounces away rather than being retained. This is not just a visual difference, it is a thermodynamic one. The color of an object determines how much radiant energy it absorbs, which directly affects its temperature. The range of colors objects can display through selective absorption is vast. A gold ring appears gold because its metallic surface absorbs blue and violet frequencies, while reflecting yellow, orange, and red. The deep blue of a sapphire comes from impurities of iron and titanium in its crystal structure that absorb red, orange, yellow, and green photons, while allowing blue to pass through and reflect. The brilliant orange of a monarch butterfly's wings comes from pigment molecules that absorb blue and green. In every case, the color you see is the leftover, the survivors that were not absorbed. This distinction matters enormously. When you say a fire truck is red, you are not making a statement about the fire truck generating red photons from some internal energy source. You are saying that the paint on the fire truck contains pigments whose molecular structure absorbs most visible frequencies and reflects the red band. Change the illumination and you change the appearance. If you light the fire truck with pure blue light instead of white sunlight, there are no red photons to reflect. The blue photons hit the paint and are absorbed, and the fire truck appears nearly black. The fire truck's redness is not an intrinsic property, the way an atom's emission frequency is intrinsic. It depends on what light is available to be reflected. Put the same fire truck under a sodium street lamp that emits only yellow light, and it will look dark and muddy, because the paint absorbs most of the yellow, and there is no red in the illumination to reflect. This is why colors look different under different lighting conditions. A dress that appears one color in daylight can look dramatically different under the fluorescent lights of a store or the warm, incandescent glow of a lamp. The object has not changed, its molecular structure is the same, but the mix of frequencies illuminating it has changed, and therefore the mix of frequencies it reflects has changed, and therefore the color your brain constructs from the reflected light has changed. The color of an object is not just about the object, it is about the interaction between the object and the light that falls on it. Now let us talk about what happens when light passes through a transparent material, because this reveals something important about how frequency and wavelength behave under real conditions. When a beam of white sunlight enters a glass prism, something visually dramatic happens. The white beam separates into a rainbow, with red light bending the least and violet light bending the most. Newton demonstrated this in 1666, and the image of a prism splitting white light into a spectrum has become one of the most iconic visuals in all of science. But what is physically happening inside the glass? When light enters glass, it slows down. Different frequencies of light slow down by slightly different amounts. Violet light slows down more than red light in most types of glass. This difference in speed causes a difference in the angle at which each frequency bends as it crosses the boundary between air and glass. The bending of light when it changes speed at an interface is called refraction. Because violet light slows more, it bends more sharply. Because red light slows less, it bends less sharply. The result is that frequencies that entered the prism traveling in the same direction exit traveling in slightly different directions, separated by their frequency. The prism does not create new colors or add energy. It simply sorts the frequencies that were already present in the white beam by exploiting the fact that different frequencies travel at different speeds in glass. The frequency of each photon, as we have seen, is unchanged by this process. The glass compresses the wavelength and slows the speed temporarily, but the frequency and energy remain intact. This means the glass is not transforming the light, it is sorting it. A prism does not paint the rainbow on the wall. The rainbow was already hiding in the beam, concealed by combination. What the prism does is give each frequency a slightly different exit angle, fanning them out so you can see each one separately. Every color in that spectrum was present in the sunlight, traveling together, indistinguishable until the glass pulled them apart. The effect is perfectly reversible. Pass the separated colors through a second prism oriented correctly, and you get white light again, because no frequency was created or destroyed. The glass merely organized what was already there. This is also what creates rainbows in nature. When sunlight enters a raindrop, the light refracts as it passes from air into water, reflects off the back inner surface of the drop, and refracts again as it exits. Each refraction separates the frequencies slightly, just as in a prism, because different frequencies travel at slightly different speeds in water. The combined effect of two refractions and one reflection spreads the sunlight into the familiar arc of colors: red on the outside, violet on the inside, and every color between. Every rainbow you have ever seen is the sun's white light being sorted by frequency through millions of tiny water prisms suspended in the air. Now there is a completely different way that light interacts with matter that produces one of the most familiar colors in human experience: the color of the sky. If you have ever wondered why the sky is blue during the day and why sunsets are red, the answer lies in a process called Rayleigh scattering, and it connects directly to everything we have discussed about frequency. When sunlight enters Earth's atmosphere, it encounters the tiny molecules of nitrogen and oxygen that make up most of the air. These molecules are far smaller than the wavelengths of visible light. When a photon encounters a molecule much smaller than its wavelength, it can be scattered, redirected in a random direction. But here is the crucial detail. The probability of scattering depends very strongly on the frequency of the photon. Higher frequency photons are scattered much more efficiently than lower frequency photons. The relationship is dramatic. The scattering probability is proportional to the fourth power of the frequency. This means that violet light, which has roughly 1.7 times the frequency of red light, is scattered roughly 1.7 to the fourth power times more efficiently. That works out to about 8 to 9 times more scattering for violet compared to red. So when sunlight enters the atmosphere from above, the blue and violet photons are scattered in all directions far more than the red, orange, and yellow photons. The red and orange photons tend to pass straight through without being deflected as much. The blue and violet photons bounce around between molecules, being redirected again and again until they are coming from every direction in the sky. When you look up at any patch of blue sky, you are seeing sunlight that has been scattered by the atmosphere. And because blue and violet photons scatter so much more strongly, the light arriving at your eye from the sky is dominated by those high-frequency photons. Your brain perceives this as blue. You might wonder why the sky is blue rather than violet, since violet photons scatter even more than blue ones. There are two reasons. First, the sun emits somewhat less violet light than blue light in its thermal spectrum, so there are fewer violet photons entering the atmosphere to begin with. The sun's emission curve is not perfectly flat across the visible range. It peaks in the green-yellow region and drops off toward both ends. By the time you reach the violet edge, the sun is simply producing fewer photons at those frequencies. Second, and more importantly, the cone cells in the human eye are not very sensitive to violet wavelengths. Our blue-sensitive cones respond more strongly to blue than to violet. The eye has evolved to be most responsive to the frequencies the sun emits most strongly, and violet falls at the extreme edge of our detection range. So even though violet is scattered more efficiently than blue, our eyes register the sky as blue because that is where our visual sensitivity peaks in the short wavelength range. A creature with eyes more sensitive to violet than to blue would see a violet sky. Sunsets are the complementary phenomenon. When the sun is near the horizon, its light must travel through a much thicker layer of atmosphere than when it is overhead. At noon, sunlight passes through roughly 1 atmosphere's worth of air. At sunset, it may pass through more than 30 times that thickness because of the shallow angle. The path through the atmosphere is so long that almost all the blue and violet photons are scattered out of the beam before it reaches you. They have been redirected sideways and upward, lighting up the sky for observers to the east who still see blue overhead. What remains in the direct beam arriving at your eye is the light that was not scattered, the lower frequency red and orange photons that survived the long atmospheric gauntlet. The sun itself appears red or orange near the horizon, and the clouds around it are illuminated by this filtered light, producing the warm colours of a sunset. The photons have not changed frequency. The red photons arriving at your eye during a sunset are the same frequency they were when they left the sun. The atmosphere simply removed the blue photons from the direct beam by scattering them away, leaving behind the red ones. The sky at sunset is nature's frequency filter, built from nothing but distance and the physics of scattering. Rayleigh scattering does not change the photon's frequency, it changes the photon's direction. A blue photon that is scattered by a nitrogen molecule is still a blue photon afterward. It still has the same frequency, the same energy, the same wavelength. It is just travelling in a different direction. Scattering is a redirection, not a transformation. But there are processes that do change a photon's measured frequency, and the most important of these, especially in astronomy, is the Doppler effect. You are probably familiar with the Doppler effect from sound. When an ambulance drives toward you, its siren sounds higher in pitch. When it drives away, the pitch drops. The siren itself is not changing. The source is emitting sound waves at a constant frequency. But because the ambulance is moving toward you, each successive wave crest is emitted a little closer to you than the previous one. The waves get compressed in the direction of motion. More wave crests arrive at your ear per second, and you perceive a higher pitch. When the ambulance moves away, the opposite happens. Each wave crest is emitted a little farther from you. The waves are stretched. Fewer crests arrive per second, and you hear a lower pitch. Light behaves the same way. When a source of light moves toward you, the electromagnetic wave crests arrive more frequently. The measured frequency is higher, shifted toward the blue end of the visible spectrum. Astronomers call this blue shift. When a source moves away from you, the crests arrive less frequently. The measured frequency is lower, shifted toward the red end. This is called redshift. The photon itself has not been altered internally. The source emitted it at a specific frequency determined by whatever physical process created it, an atomic transition, thermal radiation, whatever it was. But the relative motion between the source and the observer changes the frequency the observer measures. The amount of the shift depends on how fast the source is moving relative to the observer. A source moving at a small fraction of the speed of light produces a small shift. A source moving at a significant fraction of the speed of light produces a larger shift. The equations are well understood. You can calculate the exact speed from the exact shift. This is enormously important in astronomy. In the early 20th century, astronomers began carefully measuring the spectral lines of distant galaxies. They knew exactly where hydrogen's spectral lines should appear, because hydrogen's emission frequencies are set by the quantum energy levels we discussed earlier. They are universal. A hydrogen atom on the other side of the universe has the same energy levels as a hydrogen atom in a laboratory on Earth. The laws of quantum mechanics are the same everywhere. So when astronomers looked at the light from distant galaxies and found hydrogen lines shifted toward the red, shifted to lower frequencies than they should have been, they knew those galaxies were moving away from us. The amount of redshift told them the speed. Every familiar spectral line was displaced by the same fractional amount, confirming that the shift was due to motion rather than some unknown chemical process. In 1929, the American astronomer Edwin Hubble compiled measurements of galaxy distances and redshifts and discovered something extraordinary. Nearly every galaxy he observed was redshifted. Almost everything in the universe was moving away from us, and the farther away a galaxy was, the faster it was receding. The relationship was remarkably clean. A galaxy twice as far away was receding twice as fast. A galaxy 10 times as far away was receding 10 times as fast. This proportionality is now called Hubble's law, and it was one of the most important discoveries in the history of science. This was not because Earth occupied a special position at the center of some cosmic explosion. It was because space itself was expanding. The fabric of the universe was stretching, carrying galaxies along with it like raisins in rising bread dough. Every galaxy sees every other galaxy moving away because the space between all galaxies is growing. There is no center to the expansion. Every point in space is equivalent. Wherever you stood in the universe, you would see the same pattern, everything receding from you with speed proportional to distance. This expansion has a profound effect on photons traveling across the universe. When a photon is emitted by a distant galaxy and begins its journey toward Earth, the space it is traveling through is expanding. As space stretches, the photon's wavelength stretches with it. This is not the same as the photon moving into a pre-stretched region. The space the photon currently occupies, the space through which it is propagating at this very moment, is itself expanding. The photon is embedded in the expanding fabric, and its wavelength expands along with the fabric. Since wavelength is getting longer while the photon travels through the vacuum of expanding space, and since frequency and wavelength are inversely related for a photon in vacuum, the frequency decreases. The photon's energy decreases. A photon that left a distant galaxy as blue light can arrive at Earth billions of years later as red light or even infrared, its frequency reduced by the cumulative stretching of space over the entire journey. The photon did not lose energy to anything. No force acted on it. No material absorbed part of its energy. The geometry of the universe changed underneath it, and the photon's properties changed as a consequence. This is cosmological redshift, and it is different from ordinary Doppler shift in an important way. Ordinary Doppler shift is caused by the motion of the source through space. Cosmological redshift is caused by the expansion of space itself during the photon's journey. The galaxy that emitted the photon may not be moving through its local region of space at all. It is sitting relatively still. But the space between us and that galaxy has been expanding for billions of years, and every photon crossing that expanding space gets stretched along the way. The most extreme example of cosmological redshift is the cosmic microwave background. This radiation was emitted roughly 380,000 years after the Big Bang, when the universe cooled enough for atoms to form and for space to become transparent to light for the first time. At the moment of emission, this radiation was not microwave radiation at all. It was visible light, and even ultraviolet, glowing at a temperature of roughly 2,700 degrees Celsius. It was the thermal radiation of a hot, dense, young universe, filling all of space with an intense glow. But over the 13.8 billion years since then, the universe has expanded enormously. The wavelengths of those photons have been stretched by a factor of about 1,100. What was once visible light is now microwave radiation with a temperature of just 2.7 Kelvin, barely above absolute zero. The photons are the same photons. They have been traveling through space for almost the entire age of the universe. But their frequency has been reduced by a factor of more than 1,000 by the expansion of space. Their energy has been reduced by the same factor. Photons that were once hot enough to glow orange are now cold microwave whispers, the faintest remnant of the universe's fiery infancy, detectable only by sensitive radio antennas pointed at the sky. This tells us something important about the photon's frequency that adds a critical nuance to what we said earlier. In empty, non-expanding space, a photon's frequency is constant. It never changes. It carries the same frequency from the moment of creation to the moment of absorption. But in an expanding universe, the frequency an observer measures can change because space itself is stretching the wavelength during transit. The photon is not being acted on by a force. No energy is being taken from it by any physical process in the usual sense. The stretching is a property of the geometry of the universe itself. It is space-time that is changing, and the photon's measured frequency changes as a consequence. For astronomers, redshift is one of the most powerful tools in existence. By measuring how much a galaxy's spectral lines are shifted toward the red, astronomers can determine how far away it is and how fast the intervening space is expanding. The most distant galaxies observed have redshifts so extreme that the ultraviolet light they emitted has been stretched all the way into the infrared by the time it reaches our telescopes. We see them not in the frequencies they actually radiated, but in the frequencies those photons have been transformed into by billions of years of cosmic expansion. The photon's birth certificate, written by the atoms in that distant galaxy, has been stretched beyond recognition. But the physics is consistent. We can calculate the original frequency from the observed frequency and the amount of expansion. We can reconstruct the original emission and identify the elements, the temperatures, and the conditions that created the light, even though the light itself now oscillates at a completely different frequency than when it was born. So let us assemble the picture of what happens to a photon's frequency across its entire life. It is created with a specific frequency set by the physics of the emitting system. An atom, a molecule, a hot surface, an accelerating charge. That frequency determines its energy and, if it falls in the visible range, its physical color. The photon then travels through space. If it passes through glass or water, its wavelength temporarily shrinks and its speed temporarily drops, but its frequency is unchanged. If it encounters small particles or molecules, it may be scattered in a new direction, but its frequency is unchanged. If the source that emitted it is moving relative to the observer measures a Doppler-shifted frequency, higher if approaching, lower if receding. And if the photon crosses vast stretches of expanding space over cosmic timescales, its wavelength stretches and its measured frequency decreases through cosmological redshift. The photon does not carry a color label, it carries a frequency, and that frequency can be preserved, filtered, redirected, or shifted, depending on what happens between emission and detection. The final step in the story of a photon's color is what happens at the end of the journey, when the photon arrives at an eye or a detector, and the physical frequency is translated into a conscious experience. That translation is not as simple as it sounds. It involves biology, chemistry, and neuroscience, and it reveals that the color you see is never just the frequency of the photon. It is a construction built by your brain from incomplete information. And that construction is the last piece of the puzzle. A photon has travelled across space. Maybe it crossed a room in a billionth of a second. Maybe it crossed a galaxy in 100,000 years. Maybe it was emitted by an atom in a candle flame 3 meters away, or by a hydrogen cloud 10,000 light years distant, or by a star on the far side of the observable universe 13 billion years ago. Regardless of the distance or the time, the photon arrives carrying a specific frequency, a specific energy, stamped into it by the physics of whatever created it, possibly shifted by the expansion of space along the way. And now it reaches the final destination, a human eye. What happens next is where physics ends and biology begins, and the story it tells is as surprising as anything in quantum mechanics, because the colour you are about to perceive does not exist in the photon. It is about to be constructed, built from scratch, by the chemistry of your retina and the neural circuitry of your brain. The human eye is a remarkable instrument, but it is not a camera that passively records the frequencies of incoming light. It is an interpreter. It takes the raw physical signal, photons of various frequencies striking the back of the eye, and translates that signal into electrical impulses that the brain then assembles into the experience of colour. The translation is not straightforward. It is not a simple mapping where each frequency produces one specific colour sensation. The process involves approximation, comparison, and sometimes outright invention. Your brain does not show you the electromagnetic spectrum. It shows you a simplified model that was useful for the survival of your ancestors. The detection happens in the retina, a thin layer of tissue lining the back of the eye. The retina contains two main types of photoreceptor cells, rods and cones. Rods are extraordinarily sensitive. They can respond to a single photon in dark conditions. A single quantum of light, the absolute minimum amount of electromagnetic energy at a given frequency, can trigger a chemical change in a rod cell. The light-sensitive molecule responsible for this is called rhodopsin. When a photon of the right frequency strikes a rhodopsin molecule, the photon's energy is absorbed and causes the molecule to change its shape. This shape change triggers a cascade of chemical reactions that ultimately generates an electrical signal sent to the brain. It is an astonishing feat of molecular engineering. One photon, one molecule, one signal. But rods do not give you colour. They are responsible for vision in dim light, and they respond to a broad range of visible frequencies without distinguishing between them. A rod cell can tell you that a photon arrived, but it cannot tell you what frequency that photon had. The rod's rhodopsin absorbs photons across most of the visible spectrum. It does not care whether the photon was red or green or blue. It absorbs it and fires. In dim light, when only rods are active, you see the world in shades of grey. This is why colours seem to fade at twilight. As the light dims below the threshold where cone cells can respond effectively, your rods take over, and they report only brightness, not frequency. A red rose and a green leaf under moonlight look like the same shade of grey because your rods cannot distinguish between the frequencies those objects reflect. The colour information is there in the photons, but your rods are not equipped to read it. Colour vision comes from the cones, and here is where the construction begins. The human retina contains 3 types of cone cells, each containing a slightly different version of a light-sensitive pigment. These 3 pigment types respond to different but overlapping ranges of visible frequencies. One type, called the short wavelength or S cone, responds most strongly to light in the blue-violet region of the spectrum, peaking around 420 to 440 nanometers. A second type, the medium wavelength or M cone, responds most strongly in the green region, peaking around 530 to 540 nanometers. The third type, the long wavelength or L cone, responds most strongly in the yellow-green to red region, peaking around 560 to 580 nanometers. Notice something important. There is no red cone, no green cone, and no blue cone in the simple sense those names imply. Each cone type responds to a wide range of frequencies. The response curves overlap substantially. A photon of yellow light at 580 nanometers will stimulate both the M cones and the L cones significantly, and even the S cones to a small degree. A photon of pure spectral green at 530 nanometers stimulates the M cones strongly, the L cones moderately, and the S cones weakly. The cones do not act as narrow filters that each pass only one color. They are broad, overlapping detectors, and it is the ratio of their responses that matters. This is the heart of how color perception works. Your brain does not know what frequency a photon had. It cannot measure frequency directly. What it receives is the pattern of activation across the three cone types. A certain ratio of S, M, and L cone stimulation gets interpreted as one color. A different ratio gets interpreted as a different color. The brain reads the ratios and constructs a specific color experience from them. This system was first proposed in the early 19th century by the English polymath Thomas Young, and later developed by the German physicist Hermann von Helmholtz. It is called the trichromatic theory of color vision, and it has been confirmed by decades of experimental work. This system works remarkably well for everyday vision, but it has a profound consequence that most people never realize. It means the brain can be tricked. Because the brain relies on ratios of cone activation rather than directly measuring frequency, two physically different light stimuli can produce the same cone ratios and therefore the same color experience. This is called metamerism, and it is not a flaw in human vision. It is a fundamental and unavoidable feature of how trichromatic vision works. Any system that compresses a continuous spectrum into just three numbers will inevitably find different spectra that map to the same three numbers. It is a mathematical certainty. The only way to avoid metamerism would be to have a separate detector for every possible frequency, which would require an essentially infinite number of cone types. No biological eye does this. Every eye that has ever evolved uses a finite number of photoreceptor types, and every such eye is subject to its own version of metamerism. Here is the most vivid example. Take a photon of pure spectral yellow light at a wavelength of about 580 nanometers. This photon stimulates the L cones and M cones in a specific ratio, with relatively little S cone stimulation. Your brain interprets this ratio as the color yellow. Now, instead of spectral yellow, take two photons arriving simultaneously, one red at roughly 630 nanometers and one green at roughly 530 nanometers. Neither of these is yellow. Neither one has a frequency anywhere near 580 nanometers. But the red photon stimulates the L cones strongly and the M cones moderately, while the green photon stimulates the M cones strongly and the L cones moderately. When the brain adds up the total stimulation from both photons across the three cone types, the resulting ratio of L to M to S activation is virtually identical to the ratio produced by the single spectral yellow photon. The brain cannot tell the difference. It perceives yellow. This is not an illusion in the usual sense. The brain is doing exactly what it evolved to do. It is reading cone ratios and assigning a color. The fact that two different physical stimuli produce the same ratios is a consequence of compressing the infinite-dimensional electromagnetic spectrum into a three-dimensional color space defined by just three detector types. Information is inevitably lost. A system with only three overlapping detectors cannot fully reconstruct the original spectrum. It can only approximate it. And sometimes, different spectra produce the same approximation. Every color screen you have ever looked at exploits this principle. Your television, your phone, your computer monitor, they do not emit every frequency in the visible spectrum. They emit only three: a red, a green, and a blue, in varying intensities. By adjusting the brightness of these three primary colors at each pixel, the screen can produce virtually any cone activation ratio the brain interprets as a color. The yellow you see on a screen is not spectral yellow. There is no photon of 580 nanometers coming from that pixel. Instead, the pixel is emitting red photons and green photons simultaneously, and together they produce a cone activation ratio that is indistinguishable from the one that spectral yellow would produce. Your brain reads the ratio and perceives yellow. The sunset you watch on a screen is built from just three frequencies of light, mixed in careful proportions at each pixel, and your brain, reading the cone ratios, perceives a full range of colors as vivid and convincing as the real thing. Now, some colors you perceive do not correspond to any single frequency on the electromagnetic spectrum at all. These are colors that are purely constructed by the brain with no spectral counterpart. The most famous example is magenta. Look at a rainbow. You will see red at one end and violet at the other, with every spectral color between them. But you will not see magenta or pink or anything resembling them. That is because magenta is not a spectral color. There is no single frequency of light that produces the sensation of magenta. Instead, magenta is what your brain constructs when it receives significant stimulation from both the L cones, responding to red frequencies, and the S cones, responding to blue-violet frequencies, with relatively little stimulation of the M cones in the middle. Physically, this corresponds to a mixture of red and blue-violet photons with the green frequencies missing. No single photon can produce this combination of cone responses. It takes a mixture. And the brain, faced with strong activation at both ends of the cone sensitivity range and weak activation in the middle, invents a color that does not exist on the spectrum. Magenta is a neurological construction, a color with no wavelength. Pink is similar. It is a desaturated version of the red-blue combination, mixed with broad-spectrum stimulation that the brain interprets as whiteness. Brown is another color with no simple spectral equivalent. Brown is what the brain perceives when it receives a low-intensity mixture of red and orange frequencies in a context where brighter stimuli are nearby. The same physical light that appears orange in isolation can appear brown when surrounded by brighter light. Brown is a contextual color, created by the brain's comparison of a region with its surroundings. It does not exist as a point on the spectrum. It exists only in the brain's interpretation of relative brightness and frequency. This reveals something profound about the nature of color. Color is not a property of light alone. It is not a property of the brain alone. It is the result of an interaction between a physical stimulus and a biological system. A photon carries a frequency. That frequency is an objective, measurable, physical property. But the color you experience when that photon reaches your eye is not objective in the same way. It is constructed by a specific biological system with specific sensitivities and specific neural processing rules. A different biological system would construct a different experience from the same photon. And this is exactly what we see when we look at how other animals perceive light. Most mammals have only two types of cone cells, making them dichromats. Dogs, for example, have two cone types that are sensitive to blue and to a range spanning green through yellow. They cannot distinguish red from green. The world of a dog is not colorless, but it is less chromatically rich than a human's world. A red ball on green grass, strikingly visible to you, may be nearly invisible to a dog, because both the ball and the grass produce similar stimulation patterns in the dog's two cone types. Birds, on the other hand, typically have four types of cone cells. They are tetrachromats. The fourth cone type is sensitive to ultraviolet light, frequencies above the violet end of the human visible range. This means birds can see a dimension of color that is completely invisible to humans. What we see as a dull brown sparrow may, to another sparrow, display vivid ultraviolet plumage patterns that play a role in mate selection. Two feathers that look identical to your eyes may look dramatically different to a bird because their ultraviolet reflectance differs. The bird is seeing a channel of information that simply does not exist in your visual experience. A flower that appears uniformly white to your eyes may be covered in vivid ultraviolet patterns visible to a bee or a bird. These patterns often serve as guides, pointing pollinators toward the nectar at the flower's center. The patterns are real. They are produced by pigments that reflect or absorb ultraviolet frequencies. But you cannot see them because your eyes lack the photoreceptor that would detect those frequencies. To you, the flower is plain white. To a bee, it is an intricate map painted in a color you will never perceive. Interestingly, a small number of humans may also be tetrachromats. Some women carry a genetic variation that gives them a fourth type of cone cell with a sensitivity curve shifted slightly from the standard L cone. Research into human tetrachromacy is still ongoing, and it remains unclear how much additional color discrimination these individuals actually experience. But the possibility exists that a few humans walk through a slightly richer color world than the rest of us, seeing subtle distinctions in shades that trichromats cannot detect. The mantis shrimp may have the most complex visual system on the planet. It possesses 16 types of photoreceptor cells, far more than any mammal or bird. Some of these are sensitive to ultraviolet frequencies. Others are sensitive to polarized light whose electric field oscillates in a single plane rather than in all directions. The visual world of a mantis shrimp is almost certainly richer and stranger than anything a human can imagine. We cannot know what it is like to see with 16 receptor types because our entire conscious experience of color is built on just 3. We lack the neural architecture to even imagine what those extra channels would feel like as colors. Pit vipers and some boas have specialized organs that detect infrared radiation, the thermal photons emitted by warm-blooded prey. These infrared detectors are not part of the snake's eyes. They are separate pit organs located on the face, each containing a membrane packed with heat-sensitive receptors. When infrared photons from a nearby mouse strike the membrane, the energy is absorbed and converted into a signal that the snake's brain integrates with its visual information. The snake essentially sees a thermal image overlaid on its visible light image. In complete darkness, a pit viper can strike with precision at a warm mouse because it can see the infrared photons the mouse is emitting. Those photons are physically identical in nature to visible photons. They are excitations of the same electromagnetic field. They differ only in frequency. But the snake has evolved a detector that responds to those frequencies, and its brain has evolved the circuitry to process the signal as spatial information. The snake sees what we feel as warmth. What all of this tells us is that the visible spectrum is not a universal fact of nature. It is a biological accident. The range of frequencies we call visible, roughly 430 trillion to 750 trillion hertz, is visible only because our particular photoreceptor pigments happen to absorb photons in that range. There is nothing physically special about those frequencies. Photons just below the visible range, in the infrared, are identical in nature to visible photons. They are excitations of the same field, obeying the same laws. They just oscillate at a slightly lower frequency. Photons just above the visible range, in the ultraviolet, are equally real and equally photon-like. The only reason we draw a line between visible and invisible is that our biology draws that line. A different species with different photoreceptors draws the line in a different place. Radio photons are as real as red photons. Gamma-ray photons are as real as green photons. They are all the same particle at different frequencies. The universe does not privilege visible light. It does not consider the visible range special. The electromagnetic spectrum is a single continuous ladder, and every rung is occupied by real photons carrying real energy. We happen to have evolved 3 types of detectors that respond to a narrow band in the middle of that ladder, and we have built our entire experience of colour from the signals those 3 detectors produce. Now let us assemble the complete picture, because the story of a photon's colour is really a story that spans the entire universe, from the quantum mechanics of atoms to the neural circuitry of the human brain. It begins with emission. An electron inside an atom drops from a higher energy level to a lower one, and the energy difference is released as a single photon. The frequency of that photon is determined precisely by the energy gap. Different atoms have different energy level structures, so different atoms emit at different frequencies. Sodium emits yellow, hydrogen emits red, blue-green, and violet. Neon emits red-orange. These emission frequencies are as fixed and universal as the laws of physics themselves. A sodium atom in a laboratory and a sodium atom on a star 15 billion light-years away emit at the same frequencies. Or the photon comes from thermal radiation, where a hot object emits a broad, continuous spectrum of frequencies whose peak is determined by the temperature. Cooler objects peak at lower frequencies and appear redder. Hotter objects peak at higher frequencies and appear bluer. Or the photon comes from an accelerating charge, whose oscillation rate determines the frequency of the emitted radiation. Then the photon travels. In empty, non-expanding space, its frequency remains unchanged. If it passes through glass or water, its wavelength temporarily shrinks and its speed drops, but its frequency is preserved. If it encounters molecules in an atmosphere, it may be scattered in a new direction, but its frequency is unchanged. Blue photons scatter more than red, which is why the sky is blue and sunsets are red. If the source was moving toward or away from the observer measures a Doppler-shifted frequency, and if the photon crosses billions of light-years of expanding space, its wavelength stretches and its frequency decreases through cosmological redshift. Finally, the photon arrives at an eye. It strikes a photoreceptor cell and is absorbed. The photon's energy triggers a molecular change that generates an electrical signal. The signal from each of the 3 cone types is compared by neural circuits in the retina and brain. The ratio of activation across the 3 cone types is interpreted as a color. The brain constructs the conscious experience of red, or blue, or green, or yellow, or any of the millions of shades we can distinguish, all from just 3 numbers, the relative activation of S, M, and L cones. Colors like magenta and brown, which have no single spectral frequency, are invented by the brain from specific patterns of cone stimulation. The entire richness of your color experience, every sunset, every painting, every autumn leaf, every face you recognize by the color of their eyes, is built from this 3-channel system interpreting the frequencies of photons that may have been born inside atoms. So where does a photon get its color from? The answer has 3 layers, and all 3 are necessary. The first layer is physics. A photon's frequency and energy are set by the physical process that created it. The quantum energy levels of an atom, the temperature of a hot surface, the acceleration of a charged particle. This is the objective, measurable, physical identity of the photon. It is real. It exists independently of any observer. The second layer is journey. The frequency can be preserved, shifted, or filtered along the way. Refraction changes the wavelength in a medium, but preserves the frequency. Scattering redirects photons without changing their frequency. Doppler shifts and cosmological expansion can change the measured frequency. The photon that arrives at your eye may not have the same frequency it had when it was born, depending on what happened during its journey across space. The third layer is perception. The frequency that arrives at your retina is sampled by 3 types of cone cells. The ratio of their responses is sent to the brain, and the brain constructs a conscious experience of color from that ratio. This experience is real, but it is not the same as the frequency. It is an interpretation, a model, a biological summary of the physical signal. Different species with different photoreceptors construct different color experiences from the same photon. Colors like magenta exist only in the brain. The visible spectrum itself is just a narrow window defined by the accidents of evolution. A photon does not contain color. It does not carry a tiny label reading red or blue. It carries a frequency. That frequency was determined by the physics of the source.